Hello everyone, this is Syed Afri from section C of AML. Today my sector topic is traffic shaping techniques, the subject of computer networks, and my roll number is 24951 and 9. So we will see the brief introduction about traffic shaping. So I will start with the introduction. Traffic shaping is a network management technique used to control the volume and the timing of data packets to optimize performance and prevent congestion. It helps ensure that network traffic conforms to expected patterns, improving reliability or time sensitivity applications like VoIP or the video streaming. By regulating data flow, traffic shaping reduces packet loss and minimizes queuing delays in routers and switches. It is commonly used to enterprise networks, ISPs, and the data centers to enforce service level agreements SLAs. The traffic shaping works alongside other QoS mechanisms like policing, scheduling, and classifications to manage bandwidth efficiently. Why traffic shaping is needed? Without traffic shaping, bursty traffic can overwhelm network buffers, leading to increased latency and packet drops. Applications with steady data rates, such as video conferencing, require predictable bandwidth to maintain quality. Network links often have fixed capacities, and uncontrolled traffic can cause unfair resource usage among user or services. Traffic shaping helps avoid network congestion by smoothing out traffic bursts and aligning them with available bandwidth. It also supports policy enforcement such as limiting P2P traffic while prioritizing business critical applications. And now the key objects of traffic shaping: to regulate the rate of data transmission, to match the capacity of downstream links or services or the receivers, to reduce jitter and delay variation, which is crucial for real-time communication systems, to prevent network congestions by controlling traffic bursts before they reach bottleneck points, to ensure fair allocation of bandwidth among different users, applications or departments, to support differentiated services by allowing high priority traffic to flow with minimal delay while shaping lower priority flows. And next one is traffic shaping versus traffic policing. Traffic shaping delays excess packets by buffering them, ensuring smooth output within a defined rate limit. Traffic policing, in contrast, drops or marks packets that exceeds the allowed rate without buffering. Shaping is more suitable for applications sensitive to packet loss, such as multimedia streaming. Policing is simpler and faster but can lead to higher packet loss under bursty conditions. Both techniques are used in QoS frameworks, often in combination, to manage network performance efficiently. Leaky bucket algorithm concept. Here in this, the leaky bucket algorithm smooths bursty traffic by converting it into a steady controlled output stream. It works like a bucket with a small hole at the bottom. Data packets are added at irregular intervals but leak out at a constant rate. If the bucket fills up, incoming packets are either dropped or the queued, depending on the implementation. This mechanism enforces a long-term average rate and the limits peak traffic rates. Leaky buckets is widely used in ATM networks and as a foundational model for many traffic shapers. Leaky bucket's parameters and behavior. The bucket has a fixed capacity in bytes or packets that determines how much burst traffic it can absorb. The leak rate defines the maximum sustainable output rate, controlling the long-term average traffic flow. Short burst can pass through if the bucket is not full, but sustained high rate traffic will cause overflow. When overflow occurs, packets may be dropped or buffered, depending on system design. This algorithm is effective for enforcing traffic on contracts in virtual circuits and connection-oriented networks. Token bucket algorithm overview. The token bucket algorithm allows bursty traffic by accumulating tokens over time, which represent permission to send data. Tokens are added to the bucket at a constant rate. Each token typically corresponds to one byte or packet. To transmit data, the sender must consume tokens. If insufficient tokens are available, transmission is delayed. It is commonly used in modern routers and firewalls to shape traffic while accommodating neural or the natural traffic spikes. To transmit data, a sender must consume tokens. If insufficient tokens are available, transmission is delayed. Token bucket practical example. Suppose a token bucket has a capacity of 1 MB and refills at 100 KB per second, initially full. It allows a burst of up to 1 MB of data to be sent immediately, ideal for large file downloads. After the burst, the system can only send 100 KB per second until the bucket refills. The balances responsiveness for the short burst with long-term rate control. Many cloud platforms use token buckets logic to manage API rate limits and the bandwidth quotas. Generic traffic shapes, that is GTS. Generic traffic shapes is a Cisco proprietary method used on WAN wide area network interfaces to control outbound traffic rates. It used a token bucket mechanism to buffer and schedule packets, ensuring compliance with carrier imposed rate limits. GTS, generic traffic shaping, is especially used on series links where bandwidth must be carefully managed to avoid congestion. It supports classification of traffic in different classes, allowing prioritized shaping of critical data. GTS improves link utilization by reducing tail drops and smoothing traffic before it enters a congestion network. Frame relay traffic shaping FRTS. FRTS is designed specifically for frame relay networks to manage data flow across virtual circuits. It regulates traffic based on parameters like committed information rate CIR and the excess burst PE. FRTS uses shaping to avoid triggering frame relays congestion notification mechanism which can throttle connections. It can dynamically adjust shaping rates based on network feedback such as forward explicit congestion notification FECN. This ensures efficient use of frame relay PVCs while maintaining agreed upon performance levels. Quality of service QoS integration. Traffic shaping is a core component of QoS strategies, working with classification, marking, and queuing mechanisms. It ensures that high priority traffic such as VI, OP, or video gets preferential treatment during congestion. Shaping policies are often applied per class of service, allowing fine-grained control over different traffic types. In different server architectures, shaping helps maintain per hop behavior PHBS across network domains. Effective QoS deploys requires coordination between shaping, policing, and scheduling to maintain application requirements. Real-world applications and use cases. ISPs use traffic shaping to manage subscriber bandwidth and prevent network abuse from heavy users. Enterprises shape traffic to prioritize ERP, CRM, and video conferencing over recreational web browsing. Cloud provides apply shaping to virtual machine and containers to ensure fair resource sharing. Content delivery networks CDNs use shaping to regulate traffic during peak hours and avoid origin server overload. In IoT environments, shaping helps manage massive number of low bandwidth devices with low overwhelming core networks. Thank you for this opportunity.